Students, we are given this question. We are expected to find how many hex element of real number satisfies this equation: 7th root of x negative 5th root of x equal to 3rd root of x negative square root of x. Now you have to know, now from this equation one thing is clear: x cannot be negative. Okay, now clearly if you were to observe this equation, you can clearly see that x is equal to 0 satisfies the above equation, right? And also x is equal to 1 satisfies the above equation. So this means x is equal to 0 and x is equal to 1 are two roots satisfying the given equation. Okay, now having obtained these two roots, we have to find out if the given equation has other roots. Now you have to observe here that this is a radical equation, so I want to convert it into a polynomial equation. So for that, foremost, what we are going to do, we have to find the LCM of 7, 5, 3 and 2. Now clearly the LCM of 7, 5, 3, 2 is going to be 210, because there is no common factor for these numbers. So what I'm going to do, students, I'm going to be taking the value of x to be as some t raised to the power 210. Now when I do that, this is going to be x raised to the power, let me rewrite this, 1 over 7 negative x raised to the power 1 over 5 equal to x raised to the power 1 over 3 negative x raised to the power 1 over 2 now becomes, so in place of x I'm going to substitute t raised to the power 210. So that means this is going to be t raised to the power 210 raised to the power 1 over 7 negative t raised to the power 210 raised to the power 1 over 5 equal to t raised to the power 210 raised to the power 1 over 3 negative t raised to the power 210 raised to the power 1 over 2. Now this can be rewritten as t raised to the power 30 negative 5 divides 21 4 times and 2 times, so this is t raised to the power 42 equal to t raised to the power 70 and t raised to the power 105. Okay, now rewriting, I would get the following. So we would rewrite this. This is negative. I want to make it as positive. So what I'm going to do, I'm going to move this to the left. So when I do that, I get t raised to the power 105. I will also move this to the left. That will become negative t raised to the power 70. This would be positive t raised to the power 30 followed by t raised to the power 42 is equal to 0. Of course I need to rewrite it. Rewrite this as t raised to the power 105 negative t raised to the power 70 negative t raised to the power 42 positive t raised to the power 30 equal to 0. From here I would take t power 30 out. That would give me t raised to the power 75 followed by negative, this would give me t power 40 followed by t power 12 followed by positive 1 equal to 0. Now clearly we know that x is equal to 0 is a root and x is equal to 1 is a root, and I should suitably reflect those roots over here. Now what I'm going to do, I am going to be multiplying by t negative 1 and dividing by t negative 1. Now before I could do this, I would have to rearrange the quantity within the parenthesis in the following way. So what I'm going to do, I'm going to have t power 30 out as it is, then write t power 75 with t power 40 followed by taking a negative sign out and rewriting t power 12 positive 1 as t power 12 negative 1 equal to 0. Then I would multiply by t negative 1 and divide by t negative 1. So that's going to be returned in this following fashion. So t power 30 times t negative 1 times t raised to the power 75 negative t power 40 divided by t negative 1 followed by a negative sign. Of course you can place a parenthesis, and then this would be t raised to the power 12 negative 1 divided by t negative 1 times equal to 0. Now clearly from here t is equal to 0 is a root and t is equal to positive 1 is a root. Now the only thing is that we need to make sure how to get the other roots. So for that our focus should be on the quantities within the parenthesis. We need to have this very important formula, which is t raised to the power m negative 1 divided by t negative 1 can be represented as t raised to the power m negative 1 positive t raised to the power m negative 2 plus etc., and it goes up to positive 1. So this is a representation. So using this representation, t power m negative 1 divided by t negative 1 equals t raised to the power m negative 1 plus t raised to the power m negative 2 plus etc. plus 1. Using this representation, I'm going to rewrite the quantities. Now clearly t raised to the power 12 negative 1 divided by t negative 1 is going to be started with, you reduce from m1, so it's going to be starting with t raised to the power 11 positive t raised to the power 10 plus etc. plus 1. This is going to be for t raised to the power 12 negative 1 divided by t negative 1. But for t raised to the power 75 negative t power 40 divided by t negative 1, we will have to remove this t power 40. So if I were to remove this t power 40, then I would have t raised to the power 35 negative 1 divided by t negative 1. So this is what I would be getting. Now using this formula, I can rewrite t raised to the power 35 negative 1 divided by t negative 1 as t raised to the power 34 plus t raised to the power 33 plus etc. plus 1. This will be the last term. So what I would do, I would now place all these quantities into the parenthesis. So this is going to be t raised to the power 30 times t negative 1 times t power 40 times t raised to the power 34 plus t raised to the power 33 plus etc. plus 1 for the first quantity, followed by negative of t raised to the power 11 positive t raised to the power 10 positive etc. plus 1, and that is equated to 0. This is what we have got. Now what I'm going to do is I'm going to rewrite this in a manner by which it would facilitate me in achieving the result. So let me do that. So I'm going to rewrite this as t raised to the power 34 followed by t power 33 plus, now if you see the term starts with t raised to the power 11. So I would proceed up to t raised to the power, if it is 11 plus t raised to the power 10 plus etc. 1. This will be the first term. So the term before this would be t raised to the power 12. Okay, so that would allow me to simplify the quantity in the way that would facilitate the simplification far more quicker. So this is going to be equated to 0. Now I'm rewriting this. This is t raised to the power 30 times t negative 1 times. Now I would multiply t power 40 with the terms up to t raised to the power 12. Okay, so that would allow me to club the other terms with t power 11 in the following fashion. So I would be taking the first terms from t34 to t12. I will write it like this, and then I would again take the rest terms from t power 11 to 1, right? Okay, and then followed by the terms t power 11 positive, t power 10 positive 1 equal to 0. So this is going to be t power 30 times t minus 1 times, of course I won't touch this term, let this term be like as it is, t power 40 times t power 34 plus t power 33 plus etc. plus t power 12. Now these two terms I'm going to be clubbing together, so this is going to be t power 51 minus t power 11 plus t power 50 negative t power 10 plus etc. I will be clubbing these two terms, plus t power 40 negative 1. Okay, this is equal to 0. Now the condition is t being greater than 1. Okay, we are looking for this condition, right? Now you have to know, now t power m is greater than t power n if m is greater than n. Have that in mind. Now this in turn means t raised to the power m negative t raised to the power n is greater than 0. So we are looking for t greater than 1. Okay, because we know that t is equal to 0 is a root and t is equal to 1 is a root. So we are not interested in those values. So we are looking for values for which t is greater than 1. So that is the important point you have to note here. Now also important point is that now t power m is greater than t power n if m is greater than n, right? So that means t power m negative t power n is greater than 0. Have that in mind. So if t is greater than 1 and if m is greater than n, such that we get this t power m negative t power n is greater than 0, then clearly we can see that t power 40 times t power 34 plus t power 33 plus etc. plus t power 12 positive t power 51 negative t power 11 positive t power 50 negative t power 10 positive etc. t power 40 negative 1, all of these would be greater than 0. Okay, so that is a very important point that we need to focus on. So this would mean there are no roots when t is greater than 1. Okay, so that is a very important observation. Now the question remains to conclude. Now clearly for t greater than 1, we have seen there are no roots, there are no real roots. Okay, so we already know 0 to be a root and 1 is another root. So according to the Descartes rule of sign, this is a very important theorem, we got to know that the number of positive real zeros of a polynomial is either equal to the number of sign changes of the polynomial function or is less than the number of sign changes. So students, we would be applying the Descartes rule of sign to the quantity within the parenthesis. Now let us rewrite it. So this is t75 negative t raised to the power 40 negative t raised to the power 12 positive 1. Now I'm not doing anything to t raised to the power 30. The simple reason being, I know that t is equal to 0 is a root and t is equal to 1 is a root. I also know that t greater than 1 has no real positive roots, okay, which we have already seen. So the only hurdle that is between us and the solution is this quantity, t raised to the power negative 75 negative t raised to the power 40 negative t raised to the power 12 positive 1. The reason I am considering this, because I want to know if there are any roots between 0 and 1. Okay, so that is the objective for studying the quantity within the parenthesis. So to do that, we would be applying the Descartes rule of sign. Now from the Descartes rule of sign, clearly I know the sign of t raised to the power 75 is positive and t raised to the power 40 is negative, t raised to the power negative, t raised to the power 12 is negative, and the constant is positive. Okay, so between plus and minus there is one sign change. Between negative and negative, that is minus and minus, there are no sign changes. Between minus and plus there is one sign change. So totally there are two sign changes. Okay, so what do we know from this? So by Descartes, clearly we can conclude from Descartes rule of sign, we can conclude the presence of at most two positive real roots. Okay, at most two positive real roots. Now you have to understand that Descartes' rule of sign just tells us the number of roots possible. It does not tell us where the roots are present. Okay, have that in mind. Now to find out where the roots are present, in other words, to find out if there is a root between 0 and 1, we would have to take the assistance of another theorem. Now to do that, I wish to draw your attention to the representation of this quantity which we did in the beginning. So that is rewriting this entire quantity in the following fashion. We obtained this t raised to the power 30 times t negative 1 times t raised to the power 40 times t raised to the power 34 positive t raised to the power 33 positive etc. positive t raised to the power 12 positive t raised to the power 51 negative t raised to the power 11 positive t raised to the power 50 negative t raised to the power 10 plus etc. plus t raised to the power 40 negative 1 is equal to 0. We had this representation when we started to show that t greater than 1 has no real positive roots. So this is the way we represented the quantity. Now you have to know that we need to now first take or assign a quantity to f of t. So what I would do is, I would take all the quantities within the parenthesis to be representing f of t, or to be represented by f of t. So let f of t be t raised to the power 40 times t raised to the power 34 plus t raised to the power 33 plus etc. plus t raised to the power 12 plus t raised to the power 51 negative t raised to the power 11 plus t raised to the power 50 negative t raised to the power 10 plus etc. t raised to the power 40 negative 1. I'm only considering the quantity within the parenthesis to be as f of t. Why? Because I already know t raised to the power 30, that t is equal to 0 is a root and t is equal to 1 is also a root. So we don't need the quantities outside the parenthesis. We need to just focus on the quantities inside the parenthesis. Now, having taken f of t to represent this, what I'm going to do, I'm going to first find out what happens when t is equal to 0. So find out what f of 0 is. This entire quantity would become 0. This is 0, this is 0. This would lead you to negative 1. So in other words, f of 0 will give you a negative quantity. Now find what happens when t is equal to 1. Now when t is equal to 1, clearly you can find f of 1. This is going to be a positive quantity. Now this will vanish, and similarly this will have no significance on this quantity which we see here. This will lead to a considerable big positive value. So clearly I can conclude that f of 1 is going to be positive. Now notice here, there is a jump from negative to positive. This is where a very important theorem comes into play, which is called as the intermediate value theorem. Now what does the theorem states? Now imagine you have a graph like this, and you have a point A and you have a point B, and it is connected by means of a continuous line. Now A is defined, B is defined, and there is a continuous line between A and B. Then according to intermediate value theorem, there is a presence of a point C that would cross the line. Okay, in other words, what they are trying to tell you is, if A and B are connected by a continuous curve or a continuous line or a continuous function, for sure you will be able to have a point C between A and B that crosses the line. So how do we understand this? Simple. I want to give you this example. Now let me just take f of x to be as x to the power 7 negative 3x to the power 5 negative 2. I want to know if the function has a root between 0 and 2. So what I want to do is, I want to find out what happens to f of 0, or what happens to the function when x is equal to 0. Clearly this would give me negative 2. Now find out what happens for f of 2. Now clearly this would be a positive value, so that value will be around 30. Now just see here, for x is equal to 0, the curve is below 0. Okay, that's a very important observation. When does that happen? When x is equal to 0. Now when x is equal to 2, the curve is above 0. Okay, so by intermediate value theorem, when this change takes place, for sure there exists some x naught element of 0 comma 2, the square bracket here, okay, element of 0 comma 2, such that f of x naught is equal to 0. That means x naught is a root of the function. Now how do we apply this? Now clearly just see the function. F of 0 is negative, f of 1 is positive, so there is a jump. The curve at t is equal to 0 is below the point x is equal to 0, or I would say the curve is below 0, and at t is equal to 1, the curve is above 0. So this would imply that there is a t naught element of 0 comma 1 such that f of t naught is equal to 0. That means t naught is a root between 0 and 1. So using Descartes' rule of sign and using intermediate value theorem, we can for sure say that there are 3 roots present for the given radical equation. Okay, so this completes